I'm glad to see I'm not the only one who cares about my pipelines. So my name is RANIZ. I am a coding architect at Factor 10. This morning I was debating whether or not to put a picture of myself up here, but I mean you can see me here. So I put a QR code to my LinkedIn there instead, if you want to see what I talk about. Factor 10 is a small consultancy in Sweden. We do remote-first work, so we operate all over the world. And I'm going to talk to you about pipeline patterns and anti-patterns today. When I talk about pipelines, I mostly mean the pipelines that we run daily, that make sure that we usually do checks before we merge things into our main branch. So I just want to take a temperature reading. How many in here run pipelines daily as part of their development flow? Well, that's great. I guess that's why you're here. So keep your hands up if your pipeline runs in more than 5 minutes. More than 15? More than 20? All right, more than an hour. That's a few hands. More than a day. So I think the worst thing a pipeline can do is a random failure after 7 hours. And I've seen those pipelines. They're not fun. The only thing you can do is hit retry, and you get one try every day. It takes a while to get your pull requests merged, if that's the case. So what I'm going to focus on, or the intention here today is to reduce 2 things, or improve 2 things, and then we get a third one as a bonus if we can. So the first thing, and for me, probably the most important thing here is this. We want to reduce boredom. That is, we want to shorten the feedback loop. We start our pipeline, we get the feedback, either if it passes or if it fails, and then we can move on and do something else. We're done with that. But we also want to reduce the frustrations. No one likes a flaky pipeline. If all you can do is retry, that's a bad thing. If a pipeline fails, it should be a failure you can do something about, something you can act on. So we will try to reduce the amount of random failures we have. And if possible, as a bonus, or it could also be your main goal, we want to do something about the environment as well. Using compute time, running long pipelines, uses up energy, energy taxes the environment. So we're going to try to save the environment as well, a little bit at least. So I have 9 anti-patterns and I think 7 or 8 patterns to go with those. And well, let's get started with the first one, anti-pattern number 1, the ritual, which is when you do everything all the time. And this, it's quite natural for this to happen because when you start a new project or you start a pipeline in an existing project, we tend to do, it's demand driven, right? So we need to run the tests before we merge our pull requests. So we make a pipeline that runs the tests. And then we add on more tests, and maybe we do some linting as well. And then we merge to our main branch. But then our project manager needs to run the product. So we add a step that also publishes an artifact at the end of the pipeline, and we run it after we merge. But then someone changed something in the integration environment, so the integration tests broke, and our product manager couldn't run the application anymore. So now we run the same pipeline every night as well to make sure that the integration tests still pass. And we might end up with a pipeline looking like this. This is our original pipeline. We also run it on merge domain and nightly. So we run the same pipeline on every PR, after every merge domain, and after every nightly. And we do all the steps all the time. We run the lint, the tests, and the integration tests for both front-end and back-end, and we publish an artifact every time the pipeline runs. Now, you probably do not need an artifact for every pull request. You definitely don't need a nightly artifact, because that's going to be the same artifact as the last time you merged to main. We probably don't need to run, or we absolutely don't need to run the linting or the unit tests for back-end and front-end nightly. because those haven't changed. Those should be only reliant on stuff that's in your code base, so they can't change. They shouldn't be able to fail from one day to the other. So there's quite a lot of waste here. So we can remove those steps. And this is pattern number 1, the right pipeline for the job, which is think about what you're doing, what you want to achieve, and make a pipeline for that. Don't reuse the same pipeline everywhere. There are other ways of reusing parts of your pipeline. You could break out the setup and the tests to depending on what platform you're on, you can break them out into composite actions or sub-pipelines or something like that you can call into, which makes that you may make a composable pipeline instead of copying the pipeline. So here we run everything except the artifact when we make a pull request. And after merge, we don't really run the lints because those shouldn't have changed. We should probably rerun the unit tests because a bad merge can happen. You can have a merge that messes up your code without it being a merge conflict. So it's probably a good idea to run the unit tests. And of course, we want the artifact. And on nightly, we just run the integration tests because the linting and the unit tests haven't changed, and we really don't need a nightly artifact. And we can do more than this because let's say you make we have a backend and a frontend here, right? Let's say you make a frontend only change. We submit a CSS change, or we add a new some new functionality in the UI. There's no real need to run the backend linting or the backend tests when we do that, because nothing has changed on the backend. We still need to run the integration tests and the front-end tests because we've changed the front-end. So there's a way to achieve this, and that's called conditional steps. So that's pattern number 2, conditional pipeline steps. So if we make a front-end only commit, for example, we hide the settings menu when you log out. Well, there's no need to run the backend lint and tests. We just run the front-end part of the pipeline, and then we run the integration tests. And the same, if we do a backend only change, in this case, maybe we add a database index. Well, then we rerun the backend part of the pipeline, but we skip the front-end parts, and we run the integration tests. You can even go one step further. If you make a documentation only change, if you have your documentation in your repository, we can skip the entire pipeline because nothing has changed. So you get a feedback loop of or whatever time it takes for your pipeline to start and then don't do anything and end, a few seconds. And that saves us time because no one wants to sit around, make a documentation change and wait for 15 minutes while the pipeline runs. And we also save some money and the environment. And how you achieve this is different depending on what platform you use. The few examples I'm going to show you of pipeline code today will be for GitHub Actions, because I think that's the most popular platform, and it's the one I was working with most recently. But you can definitely do this on, I have done all of these patterns on GitLab CI, and I'm pretty sure you can do them on Circle CI or Travis or Atlassian pipelines as well, whatever you may be using. So this is how you do it in GitHub Actions. We use a custom action here, which is called a paths filter from a user named Dorney, a very clever guy. We supply a specification of the targets we have and which file patterns you should match. So if something has changed under the backend directory, this is a glob pattern. Hopefully you're familiar with those. This action or this task sets an output that says backend has changed. And the same, if something changes in the front-end directory, we get an output saying that the front-end has changed. And then we just forward these to this job in the pipeline. So we get them from the task to the job, so we can use them outside of the job. And then we tell our pipeline that the pipeline now depends on the path filter job. So we get access to these the outputs, and it runs after the path filter. And then we can use them here. If backend has changed, run the backend lint. If the backend hasn't changed, the task is skipped. There's a fairly simple way of setting this up, and it can save you a lot of time and build time. So let's move on to pattern number 2, hoarding, which is keeping all artifacts forever. And this is definitely an issue if you produce an artifact on every pull request or every nightly job. But also, when you have a long-running project, are you really going to go back and use version 1.0.3 when you're at version 27 today? Probably not. I've never seen anyone deploy a 4-year-old version in any of the projects I've worked with, probably because that environment that it looks today won't be able to run that 4-year-old project because everything else has moved on. All your infrastructure has changed. Your operating systems may have upgraded to a point where that old binary has dependencies that are no longer present. But this is not only a problem because, I mean, it takes up a lot of space, but it's also a problem of discoverability, depending on what platform you use. So this is a screenshot from a GitHub project. I'll allow them to be anonymous. But there are 3,300 tagged Docker images in this repository. And there's a further 3,900 untagged images. There's over 7,000 Docker images in their repository. They build a Docker image on every pull request, and they push it, and it just remains there. If you want to find a specific tag here, you have to wade through 69 pages of Docker images. And it takes up around 1.1 terabytes of data, which is fairly unnecessary. There's zero reason. So you see, these have been downloaded to what says 211 times, all of them, which kind of says there's some script doing this. No one's going to look at this pull request image from 4 years ago. So clean up your stuff. It'll be easier to find the really important stuff, and your sysadmins will be happier with you because you're saving them some space. They don't need to go out and buy new hard drives every month because you produce 1.1 terabytes of Docker images. So pattern number 3, the ASTAT, which is when you order your pipeline steps in sort of natural or aesthetic ordering instead of the practical one. I've done this a lot myself, but eventually, once a project matures, you can get a feeling for, because this feels like a quite natural order, right? We do the linting, which is kind of quick. Then we compile everything. We kind of need to do that before we can run the tests. Then we run our unit tests, our integration tests, and then our end-to-end tests. We run them in the order of, because integration tests, well, that's a larger thing than running unit tests, right? So we kind of makes sense to run the unit test first, and then end-to-end tests. Those are expensive and heavy, so we run those last. But depending on your project, and in my current project, and I think in a lot of the projects I've worked in before, the integration tests are the ones to fail most often. So why do we run them all the way over here? Let's just run them first, as soon as possible. Because once the integration tests fail, we get that feedback faster. This depends a lot on your pipeline. I do test-driven development, so my unit tests almost never fails because making them pass is part of my development process. If I check in something where the unit tests don't run, I'm probably having a very bad day. But the integration test is easy to forget one because they're fairly slow to run, so you might not run the whole suite every time you develop. So they tend to be the ones that fail. So pattern number 3, failing fast. Run steps in the order that means, on average, you get the quickest feedback loop. Which brings us to pattern number 4, the one pipeline. One pipeline to rule them all, one pipeline to bind them. This is where you have one pipeline. It's not like in the ritual where one pipeline does everything. This is just one pipeline does everything. It can look like this. We have backend and a front end. We do setup, linting, compiling, unit tests, and on the end we do integration tests. Nice. Nice and clear order. I mean, we need to do the backend before we can do the integration test. We need to do both backend and front end before we do integration tests. This pipeline, this is, by the way, a custom pipeline I set up for the crates.io project, which is the dependency repository for the Rust programming language. It takes 24 minutes and 40 seconds to run. That's a fairly long pipeline. So we can do things to speed it up by not running one pipeline, but instead doing 3 pipelines. So here we have one backend pipeline, one front-end pipeline, and an integration test pipeline. The backend pipeline finishes in 9 minutes. The front-end is slightly quicker, with slightly less than 9 minutes. But the longest time up here with the integration test. Now, the integration tests are done after 14 minutes instead of 24. So we saved ourselves 10 minutes of waiting for a green pipeline. We have added on around 8 minutes of total running time if you sum these all together. So let's not talk about the environment on this slide. But we get to wait a bit shorter. It costs more to run this pipeline, but I mean, my hours are cheaper or more expensive than GitHub Action build server time. So I'd rather save me 10 minutes and spend 8 more minutes on GitHub Actions. We could further parallelize this. We could run the linting as a separate pipeline, but that wouldn't really save us anything because what we're waiting for is this one. So even if we make the backend tests run in 7 minutes, we haven't gained any feedback time. It saves up some money, but you need to weigh that against the time you spend on making those improvements. Does it take you 4 hours to save 1 minute per pipeline? Is that worth it? Probably not. Antipattern number 5, gift wrapping. So this is where we use wrapper tasks to execute command line tunes. And this is, I mean, GitHub Actions comes with a lot of, I mean, it has a marketplace, right? It kind of implies that you should find stuff in the marketplace and use that. And I'm not sure you should. This is a fictitious task that I've made up, but there are very similar tasks. This task might even exist in real world. I just didn't have the time to check. It runs the cargo command, which is the Rust build system. We tell it to run the build command with the release target, use the workspace, and all features. Nice. But all this task does is create a command line that runs the cargo command line tool with some switches. And if there are some switches you want to pass to the cargo command that isn't supported, you need to make a pull request or an issue on the action repository and hope that they merge it. Or maybe there is an escape hatch where you can just tack on random arguments of your own that isn't supported. Now we have a really confusing situation where we use a tool to set flags, but then for the flags that isn't supported, we pass command line options. It's confusing. This increases the cognitive load of whoever wants to change this. Should I add a new flag, or do I need to add an argument? And what really happens? Sometimes author of these try to be clever. I mean, they know you want to use optimize. You want to optimize this as well, right? Everyone wants to optimize their build. So they tack on some optimization arguments as well. But you really didn't want them, and you weren't aware they were adding them. I've had problems with this. We use the .NET task in Azure DevOps, and that does a lot of magic for you. You think it only runs the .NET command with some switches, but it does a few things with hidden directories and adds on a few magic arguments. We were publishing our application with it, and then we were trying to do stuff with the published binaries before we packed them up into an artifact and uploaded them to the build servers. And we couldn't find the binary. It was supposed to be in one location of the file system, but it wasn't there. After we were on the publishing step, there was nothing to be found in the published location. It did some magic behind the scenes, and because it's Azure DevOps, it's closed source. We couldn't find the source, we couldn't debug it. So we switched to using just the command line tool. We just quit using the action, and we just made a run task and ran the .NET command. We told it where to put the stuff. We found it exactly where we told it to put it, and we could go on from there. And I think this is actually more readable as well. There's one line less of code, but I think it reads better as well. And with the power of YAML multiline, which, by the way, has its own website because it's so complicated, you can even structure it quite nicely so it's readable. So keep doing, don't use simple wrapper tasks for simple command. Learn your tools, use the command directly. It'll probably save you time as well because you don't really need to run a JavaScript application to build a command line. There are actions that are very useful. For example, I tend to use setup tasks, which sets up the tools that you want. In this case, this is a Python pipeline. It uses a setup Python task to set up a specific version of Python. So we know that we get the 3.11 version of Python regardless of what's installed on the runner we're using. And then I use the setup poetry, which is a build system for Python, which isn't installed by default. But then, again, we run the tool using a command line application, not a wrapper. And this all ties into keeping your pipeline simple, because that's also an antipattern, the complicated pipeline. So a complicated pipeline is essentially when the pipeline turns into a software project of its own. Pipeline tends to be, some pipelines tend to do a lot of stuff. This mostly happens when you have deployments in your pipeline, which, by the way, you should have deployments in your pipeline. Pipelines never forget to run database upgrades. Humans do. But it can grow too complex. So I think the worst offender I've ever seen was a Jenkins pipeline. Jenkins, for those of you who have never used it, allows you to write your pipeline in what they call a Jenkins file, which is basically a Groovy script. So you have the full power of Groovy at your hands. And some people do weird stuff with that. So this is the complete pipeline for all of their projects. All of their projects had a Jenkins file that looked like this. And then they had a separate software project that defined this pipeline library, which was at, say, version 4.3 at the moment. And then you just import that. The pipeline library is set as a global pipeline library in Jenkins. So it's available to all the pipelines they run. And then you just call the static method pipeline. And it does everything for every project. They even had an XML file in every project that configured what the pipeline should do. Now, if you want to change something in this pipeline, you need to make a change in the pipeline software repository. Probably a PR, get that merged, publish a new version of the pipeline jar, upload it to Jenkins, and then upgrade the version specifier up there, and then you can try to run your new pipeline on your project. Very complex to make changes, and the pipeline project on its own was 2,000 to 3,000 lines of Groovy code because it handled every project in this section of the company. So they had to have use cases for all of the features that all of the projects needed, and some XML file to turn them on and off and control which servers were deployed to what. And they had different, like some things were deployed on Oracle databases, and some things were deployed on Windows servers in the same pipeline. Keep it simple. I was tasked of migrating this pipeline to GitHub Actions, and that took quite a lot of effort just to understand, take one project, single out, what happens in the pipeline for this project, and then try to implement that in GitHub Actions. Hard to understand, very cumbersome to debug, and a pain to migrate. So instead, what you should do is pattern number 5, script your pipeline. So this is the pipeline for my Python template, which I use if I start a new Python project. You can see, well, we have the setup Python and the poetry tasks, and then I just run make, which is the old Unix tool make, with the init target and then the CI target. So the entire pipeline looks like this, and all the complexity, it's not that complex, but all the complexity are in these commands. And this is the make file for this project. So we have the init task, which just runs poetry install, which downloads all the dependencies and sets up the virtual environment. And then we have a task for linting, style check, format, type check, and test. The format is just so I can format the project easily from the command line. I don't need to remember how to run black. I just run make format, and everything gets formatted for me. And then we have the CI target down here that just depends on the style check, lint, type check, and test targets. So what this means is that when I develop locally, I can just run make CI. And it runs all the same checks that's run on the build servers. So I can be fairly sure that if I run make CI, then commit, everything passes, my pipeline will be green. If I want to debug something, I can try stuff out here, run it locally with make, and then it should work in the pipeline. I did this recently in my current project, which is a C# application. We had a fairly complex setup for our integration tests. We depend on another project, another software in the company, which needs to be running with its own database dependencies. So we did, the setup of this turned out to be fairly complex. And as soon as the pipeline step hit 5 lines, we broke that off into a PowerShell script that we could run locally. So development of that was just us running this PowerShell script for automated setup locally. And once that was working, we could then try and run the pipeline and figure out everything that's different between my developer laptop and the build servers, which also took a time, but I think we saved days because we could run all these complex steps locally because it was in a scripted file and not in a pipeline definition. Because most of the platforms you have, you can't run your pipeline locally. If you're on Jenkins, you need to run the Jenkins file on the Jenkins server. There is a project for GitHub Actions that's supposed to be able to run. It's a community project. It's not by GitHub. The goal is that you can run your GitHub pipelines locally to try them out. I've never gotten that to work beyond a simple hello world. You can run the GitLab runner locally, but I know it's a deprecated feature, so maybe they've even removed it now. If not, it's scheduled for removal. So keep your pipelines fairly simple and make sure you can run any complex stuff locally to debug them, because when they fail, you'll be thankful you can run them locally. Well, that's it for that. So Antipattern number 7, Groundhog Day. That's a movie with, is it Jim Belushi? Yeah, Bill Murray. Where he starts over on Groundhog Day every day. So this is when you start over from scratch all the time. This is a fairly new development. Back in the old days, we were using Jenkins with it kept our state all the time. That causes a lot of problems. So now we use ephemeral runners. We start a new runner, we check out everything, we do everything from scratch, and then it's killed, and we start over the next time as well. Typical pipeline, we have a setup step, downloads the source code, sets up any requirements we have. We download all the dependencies, because it's a fresh runner, right? It doesn't have any dependencies. We do the linting, we do the compiling, and we do the tests. In this case, it's also a Rust application. It takes around 12 minutes to run. So pattern number 6, to alleviate this, caching. Are you caching your pipelines? What are you caching? Because the most common thing you cache is dependencies. So we take the fetch dependency step, and we use a cache. So we restore a cache, and then we do the fetch dependency step just to make sure we didn't forget anything. And then at the end, we see if there's any updates. Typically, the caching steps don't update the cache if there was a cache hit. You only update the cache if you didn't have a cache hit, because that means something is out of date. And this saves us a lot of time, right? Well, I mean, depends on where you run your pipeline. In this case, this runs on GitHub Actions. GitHub Actions run on Azure, I think. Cloud servers with fairly high internet connections. All the dependencies are probably cached on a CDN somewhere. Might even be running the CDN on the same data center as the runners. So what we're doing is we're downloading dependencies over the network and unpack them. And what's a cache? Well, it's a giant archive of stuff that we download from a server and then unpack them. It's kind of similar, right? So fetching dependencies takes 7 seconds. Restoring the cache takes 4 seconds. And then we spend less than a second figuring out that, well, all the dependencies were here. And updating the cache doesn't do anything. So we saved around a second, 1 to 2 seconds. Are really worth it, right? You won't even notice this in your pipeline. I don't think this is a bad idea, because this isn't a cache server that is definitely on the same data center. It doesn't go out through the internet, so the connection will be stable. You won't run into flukes with internet connections, so this will generally be a more consistent way of fetching your dependencies, but it doesn't revolutionize your pipeline. What can revolutionize your pipeline, though, is caching build output. And for us, this is fairly simple. If you're a Java developer, Louis had a talk from Gradle yesterday about this. So what we do now is that we take the build output typically from the main branch, and we put that in a cache. And then we restore that before we do our linting, compiling, and tests. And the idea is that if you're using an incremental compiler, which Rust is, Gradle has done a lot of work on incremental compilation. C and C++ usually also tend to be incrementally compiled. TypeScript usually isn't, so it won't help there. But what we do is we restore the old state, and then the idea is that we should get a local experience. Because when you recompile your application locally, you don't compile everything all the time. So in this case, compiling takes 5 minutes and 36 seconds. Linting takes 2.5 minutes. But when we restore our cache, linting takes 24 seconds. Because all it has to do is to figure out, well, I've already linted all of these lines of code. I just need to check these 5 ones you added. And the same with the compilation. Well, all of our dependencies are already compiled. Those haven't changed. Most of the application is already compiled. We just need to compile our new changes and anything that depends on wherever we change that. So this saves us 4.5 minutes by uploading 2 gigabytes of cache. This is a good idea. This also helps with if you have a backend and a frontend. Probably the backend step will be really, really quick if you only just do changes on the frontend. But of course, conditional pipelines are even better. There are other things we can cache as well, which is container images. So a lot of pipelines nowadays build a Docker image. And if you do it locally and you haven't changed anything, Docker reuses your steps, says, well, this has already been done, used from cache. If you do it on a build server, there is no local cache, so it can't do that. It will have to do everything from scratch. But if we use Docker build kit instead, which is the buildx command, we can tell it to use a cache. So we create a different image, because it needs to be a different image. We tack on the cache suffix. And we tell it to use this as a cache. Typically, you only use cache 2 on the main branch, because you don't want to update the cache with every pull request. So you need some sort of conditional logic here. But what this does is, once Docker finds a command that it knows has already been done in the cache, it just downloads that. So cargo leptos is a build command, a build tool for front-end Rust applications. And it takes around 6 minutes to build. But in this case, we've already built that on the main branch. So we're just telling it to use the cache, and it takes 8 seconds, because it's only downloading the layer where this has already happened. And then we get to the new change, which is another tool we install. And of course, that hasn't happened yet, because that's what I added. So it goes on doing that. But this saved us around 8 minutes, because all the steps prior could be fetched from the cache. And we can reuse this for pattern number 7, tooling images. So the idea here is that we have 2 pipelines, one for backend and one for integration tests. And we build a tooling image first. So instead of installing our cargo leptos in the backend step and in the integration tests step, we build it once, store it as a Docker image, and then we use that Docker image to run our pipeline, saving us 6 minutes. But if we combine this with conditional steps, we can even check that, well, if the tooling image hasn't changed, we can just use the one from the main branch. So the main branch builds the image, stores it in a repository, and then a PR comes in. It hasn't changed anything in the tooling image, so we just use the tooling image from main. There's no need to build the tooling image here. We're saving 12 minutes on our full pipeline. And once a PR comes around that maybe upgrades the version of cross, well, then we build the image, use the cache, so we only have to do the last step. Tooling image, we get a new tooling image with that we use in the backend integration test for that PR pipeline. And once it's merged to main, it's built again, and now it's stored as the latest. This means that most of the times, because you generally don't touch your tooling images that often, you will have all the tools you need at the time it takes to clone a Docker image, which in this case for this image was 20 seconds instead of 6 to 8 minutes it takes to install all the dependencies. But this also means you have an opportunity for antipattern number 8, interference, where you collide with other pipelines, typically other concurrent pipelines. And this can happen if you use a shared resource, but aren't careful with how you use it. So in this case, we have our pipeline that builds an image, uses that for the backend, frontend, and integration tests, but we submit it, we build it with the latest tag all the time. We always build the latest tag. So this is one PR, runs a pipeline, builds the image, and then goes on to build the frontend and backend. But while we're running the backend and frontend pipelines, before the integration test is run, another pipeline starts, and it builds its image, and it pushes it to the latest. And that is pushed before the backend pipeline finishes. So what happens now is that the integration tests on the first pipeline run on the second pipeline's tooling image, causing it to fail. And now you have to hit the retry button, because there's nothing you can do. So when you're using shared resources, it could be Docker registries, it could be if you have an on-prem database that you need to use for your testing, you should use test containers if possible. But sometimes your databases or other shared resources aren't available in containers. Make sure you use them with randomized identifiers. Typically the GitHub SHA, the Git SHA, is a good idea to use as an identifier, because that is unique in your repository. And it's always available through various environment variables. So just be careful when you try to optimize that you don't make collisions instead. So last antipattern, I think. Antipattern number 9, overloaded. Running your builds on underpowered machines. Don't run your build agents on Raspberry Pis. They're not up to snuff. I think this is a quite common problem because people tend to be cheap. Oh, we don't need fancy large build servers. We can buy an Intel NUC or a Mac Mini and run it on that. But in the end, you're paying more because developer time costs more than hardware. So I have a few rules of thumb for build agent sizing. First off, the build agent should be at least as powerful as the least powerful developer machine. Take an inventory of your developer machines. What's the least amount of RAM you have, the least amount of processors? Make your build servers use that. Because if the developers can run your builds, then you're pretty certain that the build agents can run them. And ideally, the build agent should be at least as powerful as the most powerful developer machine. Because then you're certain that not only can they run them, they probably run it faster than it does on the developer machines, which is always a nice plus. I mean, we want that short feedback loop. And you can, at least on GitHub and GitLab, you can scale your builders. If you don't do anything, you get a default builder size, but they have been adding on different variations of these build agents lately. I think on GitHub there are 8 different sizes. I think the largest one has 128 gigabytes of memory, which should be able to compile pretty much anything I've ever worked with. So take a look at that. And if the build fails because of a lack of resources, just beef up the build agent. Don't spend hours trying to make your build use less resources by staggering tests or imposing limits on your database containers. Just beef up the build agent. Build agent time is cheaper than your time. And if the available build agent configurations aren't sufficient, consider rolling your own. So you can always run your own agents, regardless of, I think, all the platforms I've worked with, you can host your own runners. And should you? Well, it gives you full control. You can decide what hardware, what resources, how many virtual CPUs, how much RAM, what disks. If you need a graphics card, you're completely free to add on that. But it also means you need to maintain them. You need to manage operating system upgrades. You need to fix broken hard drives. You need to upgrade the runner software. But it allows you to right size. Again, you can choose exactly the resources you want. If you need 33 gigabytes of RAM, you can assign that to a virtual machine. But you also need to manage scaling. So the one major thing about using a cloud build system is that you have pretty much infinite parallelism. You can always spin up a new GitHub Actions workflow in parallel. It will run in parallel. I don't think I've ever seen a queue on GitHub Actions. But if you run in a local data center, maybe you only have 4 runners. Well, if you have 4 runners, you can't run 5 pipelines in parallel. So the possible benefit of breaking out into a 5th pipeline will be lost because that pipeline will just run after another pipeline. So it will probably be slower. So this means you need to manage scaling. If you do it in a local data center, you need to have, probably you will have all your agents running sized after the maximum amount of parallelism you want to avoid queues. If you run in the cloud, you can set up auto-scaling. I've done this both for GitHub Actions and for GitLab CI, where you basically scale your build agent cluster by demand. It can add on a bit latency because sometimes you need to start up a new server, which can take a few minutes of waiting. But if you do it correctly, you can usually scale up before demand hits and then scale down afterwards, so your developers barely will notice, and you will keep cost under control, because that's the one thing. On the other hand, you can save a lot of money by running your own builders. A virtual server on Amazon without any commitments costs about 1/10 of what a GitHub Action Runner costs if we go by hour. But there's cost to managing them as well, so you need to balance that. Do you already have an operations department that's really good at this? Well, the cost probably won't increase that much, and you can save money by running your own. But if you're a small developer team and you're not used to operating cloud solutions in this way, the cost can run away from you, and it becomes a lot more expensive to run your own than using what's available. As I said, there are ways of utilizing on-demand resources in the cloud as well. I've set up, there is a recipe, I think, for GitLab CI on Amazon using Amazon Lambda and Fargate, which are both pay for what you use, instant on demand. And I've set up GitHub Actions on Kubernetes, where you can have auto-scaling depending on what provider you use. So, what's next in the field of pipelines? There are 2 projects I think you should keep your eyes on. They're called Dagger and Earthly. So they're both built based on the same idea, and that is, you remember when we used BuildKit for caching the Docker images? They use BuildKit as well. So it's kind of a hybrid between a pipeline and a Docker image. It's like if you built your application inside of a Docker file. You get the caching for all the steps that haven't changed, except these do it with a pipeline specification instead and use Docker build kit under the hood. In Dagger's case, you write program code. They use programming languages. I think they use Java, C#, and Python. I'm not quite sure if there is more than that. And Earthly uses their own file format, which is a blend of a Makefile and a Docker file, where you define your steps in different jobs that can depend on each other and build parallel and fetch artifacts from each other. You get caching for free here and conditional steps, because if nothing has changed in the backend, those steps will be used from cache. So you can make really simple performance pipelines with these. Another selling point is that they can run locally. Both Dagger and Earthly have a local command. You just run Earthly on your Earth file, and it runs your pipeline on the targets you selected. Same with Dagger. They also have cloud services where you can run your pipelines, but you can use these on GitLab CI and GitHub Actions by essentially using the command line to run the pipeline in another pipeline platform. I haven't used these for real. I've only toyed a bit with them. I haven't used them in a real project, but I will as soon as I set up a new pipeline somewhere. I will try. I'm leaning more towards Earthly than Dagger, because I think introducing a programming language in a pipeline kind of leads to where it becomes its own software project. On the other hand, you can run it locally, so maybe it's not that big of a deal. But Earthly is way more limited in what you can do with its syntax, so it kind of encourages you to use local scripts instead of putting everything in your Earth file. So let's summarize, because I only have 4 minutes left. The Antipatterns then. Doing everything all the time, don't do that. Do one pipeline per job. Figure out what it should do and do just that. Don't hang on to all your artifacts. Take a look at your pipeline and see what's the most practical ordering to reduce the feedback loop. With what jobs fail most, put them first or as early as possible. Don't use one pipeline for everything. Split it into multiple pipelines, and you can reduce the feedback loop. But don't split it too much, because you might end up in queues, and it might not give you anything. Don't use simple wrapper tasks. Build your own command lines. Don't write complicated pipelines that turn into their own projects. They will be hard to manage. And if you want to migrate to another platform, you have a lot of work to do. Use caching as much as possible, but try to think if it actually saves you anything. Don't cache stuff that's just for caching. Make sure that it's actually beneficial to cache it. And if you use any shared resources, please make sure that you don't interfere with any other concurrent pipelines. Make sure that whatever you use is uniquely yours. And again, make sure you have the right build servers that can run your pipeline. And that's it for me. If you want to reach out, you can find me on these. The QR code goes to my LinkedIn. If you have a pipeline that runs in 7 hours, I'd love to talk to you and see if we can do anything about it. Otherwise, if you have any questions, just come up and talk to me, because we're running out of time. Thank you.